For this review session, I'm going to go through some of the problems on the old exams that I posted. I'll work through some of them and I'm going to post solutions for other ones. By the end, we should manage to get ourselves a full set of problems for you to study. First question I'll go through is from the winter 2008 exam. A 1 kilogram block is attached to a spring that has spring constant K. Notice we don't know what K is. It's oscillating with a frequency of 2 Hertz. It goes back and forth 2 times every second. It's released from rest with a displacement of 0.15 meters. This is telling us that the amplitude is 15 centimeters. Let's make a list of the things that we know. M equals 1 kilogram. Working 3 sig figs here. Frequency is 2 Hertz. Right off the bat, we might notice that if we know frequency, we can calculate period, that's 1 over f. We can calculate angular frequency, that's 2 pi f. And amplitude is the position it has when it's not moving, that's 0.150 meters. Part A, what is the spring constant of the spring? So let's think about the equations we know. One equation that I know that has spring constant in it is that omega is the square root of k over m. That means that k is going to be omega squared times m. If I could find my omega, then I could find my k. So why don't I find my omega? Omega equals 2 times pi times f. 2 times pi times 2 hertz equals 4 pi radians per second, or 12.6 radians per second. We'll put this in for our expression we had for K. Multiply by our mass, and we get a K value of 158 newtons per meter. Okay, that's part A. Part B, what is the maximum speed of the mass? So for this one, I'll remember that my equation for maximum speed, V maximum, is equal to A times omega. My amplitude is 0.150 meters. My omega is 12.6 radians per second. Put that in the calculator, we get 1.88 meters per second. So there's my maximum speed. That happens when it's at the equilibrium. What are the position and the velocity? Notice those are both vectors, so the sign is going to be important, of the block 2 seconds after it is released. So let's write down our equation for position. So x of t is equal to a times cosine omega t. We'll put in our a, 0.150 meters, times cosine of omega, 12.6 radians per second, times t, 2 seconds. What we get for our answer is 0.150 meters. You might notice here that x is back at the amplitude, and this does make sense. Our frequency is 2 Hertz. It means our period is 0.5 seconds because period is 1 over frequency. Time of 2 seconds, that's the same thing as 4 periods. So 2 seconds later, it's gone once, twice, 3, 4 times. It's back where it started. Thinking about that, you might be able to guess the velocity before you do a calculation. V of t is minus a omega sine omega t equals minus 0.150 meters times omega, 12.6 radians per second, times sine of 12.6 radians per second, times 2 seconds, to give us 0 meters per second. When our oscillator is at the amplitude, it's not moving. That's where it turns around. One last thing to point out here, we're doing sine and cosine, so we need to put our calculator in the correct mode. When we're doing this oscillation stuff, we always use radians mode, and another clue to that is that our omega is in radians per second. That's an indicator that we need to use radians mode.